zeros of normalized combinations of derivatives of Riemann-Xi function. Okay, thank you for having me speak. So whatever I'm going to talk today is a joint work with Amita Malik, Nicholas Robles, and my advisor Alexandru Zaharescu. So to start with, we have the Riemann zeta function, which is defined for real s greater than 1. And we know that this can be meromorphically continued to the whole of complex plane. And the Riemann-Xi function, which is also the completed Riemann zeta function, is an entire function and has the same zeros as the non-trivial zeros of the Riemann zeta function. And the Riemann hypothesis says that all the zeros of the Riemann-Xi function lie on the critical line real s equals half. I guess there's no need to write the Riemann hypothesis, but just for completion. So a number of impressive results have been obtained for the zeros of Riemann zeta function or the zeros of Riemann-Xi function. To start with Riemann's result, which was that all the zeros of the Riemann-Xi function are in the strip 0 to 1. And if we use the prime number theorem, then this can be shown that this is strictly between 0 and 1. And Riemann also showed that there are an infinite number of zeros and computed the first few zeros, starting with, so if rho is a zero of Riemann-Xi function, then the first zero is at some 14.134 and so on. Second zero. So these were computed by Riemann. And if we consider the number of zeros of the Riemann-Xi function in a rectangular block, so say Nt is the number of zeros of the Riemann-Xi function such that theta is between 0 and 1 and gamma is inside the strip 0 to t. And if n naught t is the number of zeros of the Xi function on the strip, then an equivalent formulation of Riemann hypothesis is that Nt is equal to n naught t for all t. So an approach to the Riemann hypothesis was initiated by Hardy in 1914, where he showed that an infinite number of zeros lie on the critical line, which technically means that n naught t goes to infinity as t goes to infinity. So later, along with Hardy, Littlewood showed, so this was in 1921, Hardy and Littlewood, they were able to show that n0t is strictly greater than a positive constant c t over 2 pi. Thus putting this into a more quantitative form. And later on, Selberg improved upon this, but more importantly introducing new ideas, and showed that n naught t is greater than oh sorry 1942, my bad. So the basic idea of Selberg in proving the statement was in order to count the number of zeros on the critical line, he counted the number of intervals where this function has a zero. So he counted the size of the set such that there is a zero in this interval. And now in order to count the number of intervals of this set, he counted the sign changes of this function in each of these intervals. So instead of counting the size of E prime, he counted the size of the set. So this was changes sign in this interval. So Selberg's basic idea was to count zeros based on the sign changes of the function, real valued function psi of t. So the next breakthrough was obtained by let's see. Yeah. So the next result was in 1949 when Min explicitly calculated this constant and showed that this has to be greater than 10 to the power minus 6. So this result also appeared in the thesis, PhD thesis of Min, and a substantial progress was only made in 1974 when Zuralev proved that the constant C should be can be computed to be equal to 2 over 21, and in the same year, independently, Levinson showed that C can be equal to 0.3427. So this essentially showing that approximately one third of the zeros of Riemann-Xi function lie on the critical line. So the basic difference between Levinson's and Selberg's proof was the fact that Selberg, in order to count the zeros, he counted the sign changes of the real valued function, and Levinson subtracted the unwanted zeros from the total set. So a remark in Levinson's proof was that if you're not efficient enough, then you might encounter a negative result if you count a lot of unwanted zeros from the total zeros. So after Levinson, the next progress took place in 1983 when Conrey, improving upon Levinson and improving the techniques used by Levinson, he showed that the constant C can be improved to 0.3658. So, and in the next year, improving his own techniques, and this time using some arithmetic techniques, he showed that the constant C can be improved to 0.4088. So this was the record till 2010, and when in 2010, along with Bowie and Young, Conrey showed that the constant C can be improved to 0.4105. And soon after this, a few months later, Feng showed that this constant can be improved to 0.4128. So till date, the record is that approximately 41% of the zeros of Riemann-Xi function lie on the critical line. So now the Riemann hypothesis implies that all the zeros of the derivatives of the Riemann-Xi function also lie on the critical line, real S equals half. Implies that all zeros of the kth derivative lie on the critical line. So analogously, as for the Xi function, we can define nkt, let's call it this, which is the number of zeros of the kth derivative and again beta is between 0 and 1 and gamma between 0 and t, and similarly the number of zeros of the kth derivative on the critical line gamma between 0 and t. And analogously to the proportion of zeros for Riemann-Xi function, one can define the proportion of zeros for the kth derivative of the Riemann-Xi function, and if we call this as AKTU, which is the number of zeros on the critical line between t and t plus u over number of zeros in the critical strip between t plus u and t. So one can see that the Riemann hypothesis basically says that A0TU should be 1, and we know that by the definition of AKTU should be between 0 and 1. So in relation to this, Conrey showed a result in so this was in 1980. The date I have here is 1893, which definitely is false, so I think it should be, let me just, I think it's, I don't have it, but it's something in 80s, so let's keep it like this, 1980s. So Conrey showed that he proved a result whose implication was that if you take if t is a sufficiently large number, positive number, and if L is log t over 2 pi and u is T over 10, then his result was that the limit of the proportion AKTU as t goes to infinity approaches 1 as k goes to infinity. So this means that almost all zeros lie on the critical line for large as you increase the order of the derivative for the Riemann-Xi function. And now, so Conrey, in an immediate next paper to this, he also showed that these zeros are simple zeros by using Heath-Brown's ideas from his paper on simple zeros for Riemann-Zeta function, and he was able to give a similar result for the simple zeros of the derivatives of Riemann-Xi function. So, in the same spirit, Rezvi-Yakova, she proved a similar result for the kth derivative of Riemann-Xi function by giving an explicit constant for 1 over k square, and her result was uniform in the parameters t and k. So she has the same result but gave explicit value of the constant c attached to 1 over k square, and her result was uniform in parameters t and k. So now deviating a little bit from the kth derivative of or the Riemann-Xi function, let's go back to a result which was proved by Selberg in 1900s, where he considered combinations of the Dirichlet-L function. So the combinations he considered in his 1900, this was in late 1900s, Selberg. This was not published, it was in his unpublished notes. He considered these combinations of the Dirichlet-L function these are L functions of modulus Qj, and Kij's are primitive characters. So what he showed was these combinations of L functions, they have a positive proportion of zeros, and he was able to show that if N0Tf denotes the number of zeros of f on the critical line up to a height t, then this is greater than constant times t log t for t greater than f, and the constant depends only on So what he proved was a positive proportion of zeros for these functions on the critical line, and there is a conjecture in his paper which says that almost all zeros of f lie on the critical line. Yeah.
What is epsilon j?
Epsilon j is let me see if I have it here. Just a second.
You want a linear combination. I see the CJ. I don't understand it.
What the epsilon j is. Yeah, it's a function of log. I don't have it explicitly written, but it's some function of log. Yeah, and it also depends on the character. Okay, so inspired by the derivatives of the Riemann-Xi function, inspired by the results on the derivatives of Riemann-Xi function and such combinations, we prove a result on the zeros of combinations of the derivative of Riemann-Xi function, and the functions we consider so we consider for every positive integer A, if we look at these combinations where L, the CJs are some real number and L is given by negative log squared 2 over T over 2 pi. The presence of these coefficients Lj, so this J goes, these are finite combinations, and we needed to insert these coefficients Lj just to make sure that no one derivative dominates over the entire combination. So if we look at this function, then we proved that for any positive integer m, if we fix a vector Cm with real components such that this constant is non-zero, and analogously to the proportion of zeros for Riemann-Xi or for the kth derivative, if we define a proportion kCat for the number of zeros on the critical line for these functions in the strip on the critical line divided by the number of zeros for these functions between t and t plus u in the critical strip, this is equal to, so if we define this as t plus u then we are able to show that this proportion so we show that in kappa t, this is where this constant depends on the vector c, and this result holds true when a and t tend to infinity. So since the leading two terms are independent of the coefficient Cj's, this is ensured by the fact that we take this constant as non-zero, and we achieve, as special cases, we achieve the results of Conrey and Resvioka. So,
I'm sorry, can I just ask, what is that? It's a rho squared plus 2 over 16 in front of the 1 over a squared?
this is E square.
E squared.
Yeah.
Is that the natural?
Yeah,
Ah,
yeah. Okay. So, a few remarks on the function. So, this satisfies a functional equation because the Riemann-Xi has a functional, yeah. This one?
That's one, that ratio you wrote down. Log, 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 log.
So this is log log, oh sorry, sorry, my bad. Okay, so because the Riemann-Xi has its functional equation, one can see that this function also has a functional equation, which is and as for the derivatives of Riemann-Xi, if you take the function f, and if f has its zeros in some critical strip, has zeros in some critical strip, then all the derivatives of this function will also have its zeros in the same critical strip. Zeros in the same. And in particular, if the function satisfies the Riemann hypothesis, then its derivatives are also going to satisfy the Riemann hypothesis. So one can see this if one uses, say, for example, if one uses the induction on the order of the derivative, one can prove that if the function has its zeros on the critical line, then its derivatives also have its zeros on the critical line. Okay.
Can I ask why you take the derivatives sort of with even parity? It's a plus 2j's, and why not just a plus j?
Yeah, so it could, so the problem which we face when we compute, we want all of them to be either even or all of them to be either odd. So depending on what you start with. Yeah. Okay, so.
I have another question. I mean, you're looking at Xi rather than like the Hardy Z function.
Yeah.
Xi has got gamma factors, so I guess you need the L to J to balance the gamma factor. I mean, it seems strange to include the gamma factor as a weighting because it's exponentially decaying, or.
Yeah, so when we prove the zero-free region, if we don't include the L in the denominator, we see that it's dominated by just one of the derivatives in the combination. So.
But could you also instead look at the Hardy Z function, which is more balanced in size? You know, it doesn't have this.
And then you wouldn't have to
Possibly
include the. Okay.
That's my gut.
Yeah, I haven't thought about it, but yeah, looks like. Okay. Yeah, so if we go over the proof of this, let me just give you a brief sketch of how we go about proving. The methods are inspired by Levinson's, which was later refined by Conrey and Resvioka. So. So the first step is we prove a zero free region for the function CAT. So we show that this function is non-zero for and for sigma by the functional equation. And then using the identity FCAT for some function p, which I'm not going to write, we prove an inequality for the number of zeros of f in the critical line, and we relate it to the change in argument of the function p from t to t plus u. So we get an inequality on the number of zeros of f on the critical line and the change in argument of IT where t goes from t to t plus u. So the next step is to find an inequality in terms of the number of zeros of f in the critical strip, and an inequality on number of zeros of f on the critical strip with the change in argument of the function of this function, which is the Riemann-Xi divided by the zeta s. So we want to find, let's see, yeah, not at half plus IT, but and t between t and t plus u. So change in argument with number of zeros of f on the critical strip. So most of the zeros of f on the critical strip can be written in terms of the change in argument of this function. So once you have the number of zeros on the critical line and the number of zeros on the critical strip, you just divide the two inequalities and you get, so this is an equality and this is an inequality. You just divide and you get a relation between kappa, the proportion on one hand, and on the other hand you get a relation in change in argument of this function over h. So kappa inequality in terms of the change in argument of Ps over Hs. And using the argument principle, in order to find the change in argument of this function, you just count the number of zeros in some contour. And we don't count the number of zeros of the function v exactly, but instead, as is done in Levinson, you count the number of zeros of a mollified function psi s times vs 1 over d star, so where d star is non-zero. And psi is an entire function which does not vanish in the contour you are considering. So instead of counting the number of zeros of v, we look at the number of zeros of this function, and we get an inequality for kappa. So let's see if, oh, I have time. So maybe I'll quickly see how we, quickly show how we, what is the relation between kappa and the zeros of this function. So the mollifying function, as I mentioned, that we are interested in finding the number of zeros of this. The mollifying function we consider here is And as a remark, the mollifier which Levinson considered in his proof for the Riemann zeta function was where m is the length of the mollifier and its power of t, where theta is between 0 and half, times a polynomial of log so later, so this was the mollifier which Levinson used in his proof for the Riemann zeta function, and later he took the polynomial p to be equal to x. So the polynomial should also satisfy this condition, and this is one of them which satisfies this condition. So the mollifier, so the subsequent results on the improvement of the percentage of zeros on the critical line was basically by changing the mollifiers. So the mollifier which, for example, Conrey, Bowie, and Young used was this mollifier along with another mollifier which replicates the behavior of the inverse of zeta. So the mollifier used by Bowie, Conrey, and Young was this plus another piece of this, but with different coefficients here. So, and the mollifier which was used by Conrey in his proof for the kth derivative of the Riemann-Xi function was simply the monomial of degree r. So it was px equals x to the power r. So now, if we use Littlewood's lemma, then we can relate the number of zeros of this function with an integral involving log of this function, and then by Jensen's inequality and Cauchy squares, we can relates the number of zeros of this with the integral of the square of this function. So in conclusion, we get an inequality for kappa in terms of an integral of the square of this function. So we see that we get n to be bounded by 4 pi log j over u plus big O of u, and j over u is some linear combination of integrals AJL, where AJLs are given by one over u t to t plus u of So I'll just quickly tell you what BJs and DJs are. So this is just and evaluated at so these functions Bj and Bl are just, so we rewrite V, we break it into two parts, and we write V as some B plus chi s times ds. And so remember, V is a linear combination, and a linear combination of say VRs, and similarly B's are the linear combinations. So each of these each of these terms in the linear combination are Bj's and Dj's, and these are the linear combinations in the mollifier psi s. So this is psi rs is basically everything except CR tilde. So it's mu n over n half So the task was to approximate each of these integrals, and once you approximate these integrals and use calculus of variations, we see that these functions, we get half plus so these are AJLs. And in order to get a bound, we needed the minimum value of this, and the minimum is attained. So S here is some combination of and the minimum value of this expression here is attained when when S takes this value. And if you plug in S as this entire term gets cancelled, and you're left with 1 plus e square plus 2 over 16, 1 over a square, plus but then we needed to take a log of j over u in the kappa inequality, and if you expand, so the kappa inequality was something like 1 plus log j over u plus an error. So if you just expand the log, you get kappa to be greater than 1 minus e square plus 2 over 16 times 1 over a square. So our initial motivation to do this problem was to try to prove Selberg's conjecture on the combinations of L function. So we considered the combinations for the derivative, but now we are back to the problem of doing giving a proportion for the zeros of Selberg function, and the mollifier which we need to use for Selberg's combinations are different from all the other mollifiers which we've been using, and we need to, so instead of a combination of mollifiers, we need convolutions of mollifiers for the Selberg combinations. So that's a work which is in progress. So yeah, that's all.